Atlas 2025, Comet or Spacecraft? Full documentary. A team of Harvard astronomers, while reviewing the latest Atlas project data, detected something that defies normal physics. The object was no longer following its predicted path. Within hours, NASA's Jet Propulsion Laboratory quietly introduced a new orbital solution into its systems, without releasing any public statement. It is true that comets can shift slightly due to jets of gas released as they warm near the sun, but in this case, the variation was far too large to be explained by random natural processes alone. Internal reports began using unsettling expressions: non-gravitational impulse, stepwise accelerations, terms that sound less like the chaos of a wandering block of ice and rock, and more like the control of a spacecraft. The official stance remained silence, but the numbers told a different story. The first warnings did not come from government laboratories. They came from Bill Gray's open-source software, widely used by professional and amateur astronomers. On September 23, the discrepancies between predictions and reality stopped being noise and became a clear pattern. Atlas was ahead of schedule. Its position in the sky was so different from the expected coordinates that the system raised an alert for a possible orbital error. The warning reached the Harvard-Smithsonian Center for Astrophysics. There, using new images from the Magellan telescopes in Chile, astronomers confirmed the anomaly. Atlas was not where it should have been. The magnitude of the change forced NASA's Horizons database to publish an updated orbital solution. The correction appeared quietly, buried among routine daily updates, without any announcement. But attentive observers noticed immediately. Telescopes pointed at the old coordinates found only empty sky. When the coordinates were corrected, Atlas reappeared brighter than expected and clearly displaced from its previous orbit. To the public, there was silence. But inside Harvard, internal bulletins were more direct. Non-gravitational acceleration had been observed. That phrase cannot easily be attributed to simple outgassing. It suggested something far more deliberate. History shows that comets can behave unpredictably. Halley, Shoemaker, Levy 9, and others revealed small measurable deviations, but all of them stayed within the boundaries of known physics. Atlas, however, had broken precedent. The September deviation implied a displacement of tens of thousands of kilometers in just a few weeks. This was not a minor nudge, it was a redirection large enough to alter its perihelion. Even stranger, the data showed not a smooth continuous acceleration, as solar heating would dictate, but discrete impulses, as if someone or something was adjusting its course in controlled bursts. The odds of this happening naturally are close to zero. To reach such magnitudes, Atlas would need to release amounts of gas never seen in its spectrum. The unspoken conclusion was clear: controlled thrusts. Official reports avoided the phrase, preferring non-gravitational impulse. But between the lines, the message was the same: comets do not move this way. October 17 marked the approach to perihelion, but also a critical period. Between October 8 and 18, Atlas would vanish into the sun's glare. For those 10 days of blackout, Earth's telescopes would be unable to track it, and even space observatories would be restricted to protect their sensors. During that window, any maneuver would be invisible. When Atlas re-emerged, it might already be too late to know if the change had been natural or intentional. A leaked Harvard draft summarized it bluntly: stepwise accelerations, incompatible with random outgassing. For an academic report, such words were extraordinary, more like the diagnostics of a spacecraft than the description of a comet. The most striking phrase came near the end: artificial impulse not excluded. Meanwhile, NASA chose a lower profile. In Horizons, orbital parameters were adjusted daily, but without press conferences or official bulletins. To the casual observer, Atlas looked like any other comet with routine updates. But for those following closely, the constant corrections were themselves a red flag. This raised a deeper question. If Atlas really was maneuvering, what was its goal? Was it a deliberate signal, a course correction, or an operation we were not meant to understand? Energy calculations only deepened the unease. A deviation of just 0.1 would require an impulse of tens of meters per second. For a nucleus hundreds of meters across, that translates to gigawatts of power, comparable to the output of multiple nuclear power plants combined. Anomalies in July and August had already suggested 3 bursts of thrust, each releasing the energy of around 10 GW. For a comet, such power is inexplicable. The comparison with Swan was revealing. Discovered just days earlier, Swan showed remarkable stability, solid and shaken even under solar pressure. Atlas, in contrast, behaved like an agile body, adjusting its trajectory with precision. Some astronomers began to describe a cosmic tandem: Swan the fortress, Atlas the maneuverable scout. Different hypotheses emerged. The Explorer probe. Atlas could be an object designed to maneuver deliberately into the solar system. The course correction. September's deviation might have been a calculated adjustment before perihelion. The decoy. Atlas could be nothing more than a distraction, drawing attention while something else happens elsewhere. None could be confirmed, but all matched the data. Institutional silence only fueled speculation. At Harvard, draft articles were held back. At NASA, public statements softened anomalies into natural outgassing. Yet outside, independent astronomers organized under the banner Atlas Watch 2025. They coordinated wide-field cameras, small telescopes, and even amateur radio experiments bouncing signals off the comet's coma. During the solar blackout, every independent measurement would matter, because when Atlas reappeared, the outcome might redefine our view of the solar system: an unpredictable comet, or the first evidence of a deliberately controlled object. Why does everything spin? From protons to galaxies. Everything spins. From the tiniest proton to the largest galaxy, motion in the universe seems to follow a mysterious rule. Nothing stands still. But here's the paradox: nobody really knows why. Physicists can describe how things spin, they can measure rotation, they can predict its effects. But the deeper question, why does the universe insist on spinning at every scale, remains unanswered. Some scientists argue that spin is fundamental, built into the laws of physics. Others suggest it may only be an illusion, a byproduct of how we measure motion. And a few go even further, claiming that if we could explain why everything spins, we might uncover the ultimate law of the cosmos. Do we really understand spin, or are we just pretending with equations while the truth is still hidden? Spin in the quantum world. At the smallest scales, particles like protons and electrons have a property called spin, but this doesn't mean they spin like tiny balls. Quantum spin is stranger. It's a built-in quality of matter, like charge or mass. Electrons can have only two spin states, up or down. This simple property builds the entire periodic table of elements, determines the structure of atoms, and even explains why matter is stable. And yet, nobody can tell you what spin really is. It is not a literal rotation. It is a quantum number, a kind of intrinsic fingerprint of particles. But then the mystery deepens. Protons themselves are made of quarks, each with their own spin. When you add them up, the result doesn't match the proton's actual spin. Where does the missing spin come from? This is called the proton spin crisis, and it remains one of the great puzzles of physics. The cosmic ballet, stars and planets. When we look up at the night sky, we see not just shining points of light, but a grand cosmic ballet. Every planet spins, every star rotates, even the Earth, our home, turns once every 24 hours, carrying us through day and night. But why does this happen? The answer goes back to the birth of stars and planets. In the beginning, giant clouds of gas and dust floated silently in space. Gravity pulled them together, and as the clouds collapsed, they began to spin the same way a figure skater spins faster by pulling in their arms. This simple law of physics, called the conservation of angular momentum, ensures that rotation never disappears. Once motion begins, it carries on forever unless something stops it. The sun spins once every 27 days. Jupiter, the giant of our solar system, rotates so fast that a day there lasts less than 10 hours. Saturn, with its majestic rings, spins even faster. Every planet carries this ancient motion from the time it was born. Even stars and distant galaxies rotate, dragging their plasma and magnetic fields with them. This spin shapes their magnetic storms, their flares, and even their violent deaths as supernova. And yet, the mystery lingers. Conservation of momentum explains how spin survives, but not why it began in the first place. Why did the first cloud start rotating at all? Was it just chance, or does spin reveal a deeper design of the universe? Galaxies in motion. If planets and stars spin, what about galaxies? The answer is breathtaking. Entire galaxies rotate, like cosmic whirlpools of billions of stars. Our own Milky Way spins once every 225 million years. From our perspective, it seems almost frozen, but on the scale of the universe, it is turning like a giant wheel. Stars, dust, dark matter, and even black holes all move together in this vast rotation. But here's the puzzle. Galaxies spin too fast. According to the gravity of their visible matter, they should fly apart. The stars at the edges rotate at almost the same speed as those near the center, something Newton's laws cannot explain. This mystery led to one of the most important discoveries in modern science: dark matter, an invisible substance that makes up most of the galaxy's mass, holding it together like an unseen glue. Without dark matter, galaxies would simply scatter into space. And it doesn't end there. Supermassive black holes. The universe itself? Does everything spin? When we step back from stars and galaxies, we face the ultimate question: does the universe itself spin? Some scientists have searched the cosmic microwave background, the faint afterglow of the Big Bang, for signs of global rotation. So far, the results show the universe looks the same in every direction, with no clear evidence of spin. And yet, some theories suggest that if the universe did rotate, it could explain mysteries like dark energy or the alignment of distant galaxies. Imagine the entire cosmos turning like a giant wheel. But here's the paradox: if the universe spins, we are inside it, turning with it. How could we ever truly prove it? Spin and the hidden laws of physics. Spin is not just motion, it is a window into the hidden laws of reality. From the smallest particles to the largest galaxies, spin reflects the conservation of angular momentum. Once something begins rotating, it never stops unless acted upon. This simple principle explains why stars keep spinning, why planets continue their daily rotations, and why galaxies whirl across billions of years. But hidden within this law are deeper mysteries. The proton spin crisis showed us that even basic particles don't behave as expected. The same laws that stabilize atoms also shape cosmic structures. Some physicists believe spin could be the thread connecting quantum mechanics to cosmology, the missing piece in the search for a unified theory. So the question becomes, is spin just a rule of motion, or is it the secret architecture of the universe itself? Philosophical reflections on spin. From protons to galaxies, spin is everywhere. But what does it mean? Spin could be telling us that motion is fundamental, that the universe is not built on stillness, but on constant change. Or perhaps it reminds us that we only see part of the truth, that rotation is an illusion created by our perspective. Philosophers of science argue that if everything spins, then maybe the cosmos is not a static machine, but a living, dynamic system. A universe that dances, not one that merely exists. The mystery of spin may never be fully solved, but perhaps that is the point. The more we search, the more we realize the universe is not just something to be explained, it is something to be experienced. From the tiniest proton to the largest galaxy, everything spins. Spin is not just a property of matter, it is the rhythm of the universe itself. We can measure it, describe it, even predict it, but the deeper question remains unanswered. Why does the universe insist on spinning at every scale? Perhaps spin is just the result of physical laws, an echo of the Big Bang carried forward through time. Or perhaps it is something more, a hidden code, written into the fabric of reality. In the end, the mystery of spin is not just about particles or galaxies, it is about us. Because if everything spins, then so do we, part of the great cosmic dance, woven into the endless motion of the universe. The universe does not stand still, and maybe, neither should we. The proton mystery. What physics still can't explain? At first glance, the proton seems like the simplest thing in the universe. It is the tiny, positively charged particle found at the heart of every atom, the foundation of all matter. Every star, every planet, every living being, everything you see around you is built upon protons. And yet, behind this apparent simplicity hides one of the greatest unresolved mysteries in modern science. The proton, the particle we thought we understood best, continues to puzzle physicists. Its size doesn't match our measurements. Its mass comes from nowhere. Its stability appears absolute, and yet our theories suggest it may not last forever. If we cannot explain the proton, how can we claim to understand the universe? Today, we embark on a journey into the heart of the proton, a journey that begins with the building blocks of atoms and leads us to the very limits of physics itself. And yet, some scientists argue that the proton might not even be real in the way we imagine. Nobody has ever seen a proton directly, it only exists as a model in our equations and experiments. So, is the proton truly real, or just a useful human invention? What is a proton, really? The proton is not a solid ball of matter. It is a swirling dance of three quarks bound together by invisible forces. These forces are carried by gluons, massless particles that tie the quarks together with unbreakable strength. Inside the proton, quarks never sit still. They vibrate, they move. They exchange gluons in a chaotic storm of energy. In fact, if you could look inside a proton, you wouldn't see three neat particles. You would see a blur of quarks and gluons appearing and disappearing in a quantum haze. It is this chaos, this storm of energy, that makes the proton so mysterious. The mystery of mass. Here lies the first great puzzle. The three quarks inside a proton are surprisingly light. If you add up their masses, they account for only about 1% of the proton's total weight. So where does the rest of the proton's mass come from? The answer, physicists believe, lies in the energy of the gluons and the quantum storm inside the proton. Einstein's famous equation, E equals mc, tells us that energy and mass are interchangeable. The wild motion of gluons and virtual particles inside the proton creates almost all of its mass. This means that the weight of the universe, the very matter that forms stars, planets, and people, doesn't come from matter itself, but from pure energy locked inside the proton. It is a breathtaking idea. Matter is an illusion, built from energy storms we barely understand. The proton radius crisis. For decades, scientists believed they knew the size of the proton. It was measured again and again, always yielding roughly the same value. But in 2010, a shocking discovery shook the world of physics. When researchers used muon's heavier cousins of electrons to probe the proton, they found it to be 4% smaller than expected. The result was so different that it sparked what is now called the proton radius crisis. Two different measurements, both precise, both trusted, and yet they disagreed. It was as if nature had been keeping a secret from us all along. Some say the problem lies in our methods. Others believe it might hint at new physics beyond the standard model. If the proton radius puzzle cannot be solved, it means our very picture of the atomic world may be incomplete. Stability and decay. Another mystery lies in the proton's stability. Every particle in the universe eventually decays into something else. Neutrons outside the nucleus decay in just 15 minutes. Even stars collapse, galaxies fade, black holes evaporate. But protons? They appear immortal. In every experiment, protons have never been seen to decay. According to theory, their lifetime is at least 10 years longer than the age of the universe itself. And yet, some grand unified theories predict that protons must decay eventually, turning into lighter particles in a burst of energy. If that is true, then even the matter that makes up your body will one day dissolve into pure radiation. The paradox remains: are protons eternal, or is their death simply too slow for us to witness? Protons and stars. Without protons, there would be no stars. Every ray of sunlight, every flickering star in the night sky, is powered by the collisions of protons deep inside stellar cores. This process is called the proton-proton chain reaction, and it is the engine of the universe. In the heart of the sun, at temperatures of 15 million degrees, protons smash together with unimaginable force. Normally, their positive charges repel each other, but under such heat and pressure, they can fuse. When two protons collide, one transforms into a neutron, creating a deuterium nucleus. Step by step, more collisions build helium, and in the process, vast amounts of energy are released. This is the fire of the stars. Every beam of sunlight that warms your skin is born from proton collisions. Every galaxy glows because of the relentless work of protons and countless stars. And one day, when stars exhaust their fuel, protons again decide their fate. In massive stars, they collapse and explode in supernova, scattering elements across space. In smaller stars, like our sun, they quietly fuse until the light fades. It is not an exaggeration to say, protons are the true architects of the cosmos. Experiments and colliders. If the proton hides its secrets inside a storm of quarks and gluons, how can we hope to uncover them? The answer lies in the most powerful machines ever built by humans: particle colliders. At CERN, the Large Hadron Collider LHC accelerates protons to nearly the speed of light and smashes them together with unimaginable force. For a fraction of a second, the collisions recreate the conditions of the early universe. These experiments allow scientists to peer inside the proton not by looking directly, but by studying the debris left behind after collisions. Like smashing a watch to understand its gears, we learn about protons by breaking them apart. Yet, even with all this power, mysteries remain. The distribution of quarks inside a proton seems to shift depending on how we probe it. Sometimes gluons dominate, sometimes quarks appear in strange configurations. It is like the proton changes its identity depending on how we look at it. Some experiments even suggest that the proton may contain particles we haven't discovered yet, hidden layers beyond the standard model. The collider becomes not just a tool of observation, but a portal to the unknown. Fundamental theories. The proton is not just a particle, it is a test for our greatest theories. The standard model of physics tells us that protons are made of quarks and gluons, bound together by the strong nuclear force, but when we try to calculate the exact properties of the proton, its mass, its spin, its radius, the numbers never fully agree with experiments. Quantum chromodynamics, or QCD, is the theory that governs how quarks and gluons interact. It is one of the most beautiful and complex mathematical frameworks ever built. Yet even QCD cannot fully predict the behavior of the proton. We can simulate parts of it with supercomputers, but the full solution remains out of reach. Some scientists suggest that protons may even interact with dark matter, or reveal cracks in the standard model itself. If so, then the humble proton could hold the key to a deeper theory, a unification of forces, or perhaps even the next great revolution in physics. The mysteries of the proton are not small. They stretch from the tiniest scales of quarks to the largest questions of the cosmos. A philosophical view. Imagine this: every star, every galaxy, every living being, all are made of protons. They are the bricks of the universe, and yet, after decades of research, we still cannot explain them completely. What does it mean if we do not understand the very matter we are made of? Perhaps the proton is reminding us of something deeper, that the universe is not a finished puzzle, but a living mystery, that the smallest things can hold the greatest secrets. Some philosophers of science even argue that the proton shows the limits of human knowledge. If we cannot understand the building block of matter, maybe the universe will always keep part of itself hidden. But others see it differently. The proton is a challenge, an invitation, a signal that the story of science is far from over, and that the greatest discoveries still lie ahead. The proton may be tiny, but its mysteries are enormous. Its mass seems to come from nowhere, its size refuses to be pinned down, its stability appears eternal, and its behavior challenges the best theories of modern physics. We once thought we understood the atom, but the closer we look, the more the proton reminds us that reality is stranger than we ever imagined. From the cores of stars to the edges of galaxies, protons are the architects of the cosmos, but they are also riddles waiting to be solved. And so, the journey continues. As long as protons exist, which may be longer than the universe itself, humanity will keep searching for their truth. Because in solving the mystery of the proton, we may also uncover the deepest truths about ourselves and the universe we call home. The universe is full of mysteries. Today, we'll explore 5 incredible space facts that science still cannot fully explain. Fact 1: Oumuamua. In 2017, astronomers detected Oumuamua, the first known interstellar object passing through our solar system. But it behaved unlike any asteroid or comet ever seen. Its strange acceleration and elongated shape sparked a thrilling debate. Was it a natural rock, or could it have been an alien probe? Fact 2: The Fermi Paradox. The Fermi Paradox asks a haunting question. If there are billions of stars with planets in our galaxy, why haven't we found extraterrestrial life? Are we truly alone in the universe? Or are we simply not looking in the right way? Fact 3: Dark matter. 85% of the universe is made of something we cannot see, dark matter. It doesn't emit light. It doesn't interact with atoms, yet it holds entire galaxies together. Nobody knows what it really is, making it one of the greatest puzzles in modern physics. Fact for fast radio bursts. In the last decade, astronomers have discovered mysterious fast radio bursts, powerful signals from deep space that last only milliseconds. Some repeat, some appear only once, and their origin remains a cosmic mystery. Are they natural phenomena, or something more? Fact 5: Ultra-high energy cosmic rays. Sometimes, particles strike Earth with unimaginable energy. A single proton can arrive carrying as much force as a baseball pitch. How the universe accelerates these particles to such extreme speeds is something science still cannot explain. These are just a few of the space mysteries waiting to be solved. Which one fascinates you the most? Tell us in the comments. And don't forget to subscribe for more cosmic discoveries. These were just 5 space facts, but there's much more. The full documentary with 12 incredible mysteries will be released in just a few days. Stay tuned, you won't want to miss it.
Strange visitors from beyond our solar system. What if the objects we see in the sky are not from our solar system at all, but visitors from distant stars? For centuries, astronomers assumed that comets and asteroids belonged only to our sun's family. But in the last few years, we have discovered something astonishing. Real interstellar travelers, objects that cross the void between stars and briefly pass through our cosmic neighborhood. These visitors carry secrets of other worlds, and perhaps even hints of something more. Oumuamua, the first interstellar guest. In 2017, telescopes in Hawaii detected a strange, elongated object rushing through the solar system. It was named Oumuamua, Hawaiian for a messenger from afar. Oumuamua did not behave like anything we had ever seen. It was cigar-shaped, tumbling through space, and showed no comet tail. Yet it moved in ways that could not be explained by gravity alone. Was it an asteroid? A comet? Or could it have been something artificial? Some scientists, including Avi Loeb from Harvard, suggested it might even be an alien probe. Most disagree, but the mystery remains unsolved. Oumuamua left our solar system quickly, vanishing into the dark, leaving only questions behind. II Borisov, the true interstellar comet. 2 years later, in 2019, another visitor appeared. Unlike Oumuamua, this one looked familiar. A glowing nucleus with a bright, icy tail. It was named II Borisov, after the amateur astronomer Gennady Borisov, who discovered it. But make no mistake, Borisov was no ordinary comet. Its chemical fingerprint revealed subtle differences. Unlike the comets born near our sun, it was, without doubt, a traveler from another star system. For the first time, astronomers could study an interstellar comet up close and confirm that the universe is full of such wanderers. (3.1) Atlas, New Mysteries. In recent years, astronomers have tracked a third interstellar candidate, III Atlas. Unlike Borisov, Atlas seemed unstable, fragmenting as it moved. Some astronomers suggest it might be a broken shard from a much larger body. Atlas is still under study. Its unusual trajectory and faint glow suggest it could teach us more about how interstellar debris travels through space. We may not yet know its true nature, but it proves that interstellar objects are not rare accidents. They might be common visitors. What do they reveal about the universe? Each of these objects is more than just rock and ice. They are messengers from distant stars, carrying within them the chemistry and physics of alien worlds. By studying their composition, we learn about how planets form around other suns. By tracing their orbits, we see how gravity shapes not just our solar system, but the galaxy itself. And perhaps, one day, we will find a visitor that is not just natural, something that carries a signature, not of chance, but of design. A philosophical view. Oumuamua Borisov Atlas. 3 names that remind us the universe is not empty. It is alive with motion, and sometimes it sends us unexpected guests. Maybe these are just rocks, fragments of faraway systems. Or maybe they are the first hints that we are not alone. What do you think? Are these interstellar objects simply natural debris? Or could one of them be a message, a sign, or even technology from another civilization? Something is wrong with distance. Something about the universe does not add up. We are told the universe is 13.8 billion years old. We are told nothing can travel faster than light. And yet, when we look into the deepest reaches of space, we see light arriving from regions that are over 46 billion light years away. That number alone should make us pause. How can light travel farther than the age of the universe allows? How can distance grow faster than time itself? And why does the universe seem to be hiding most of itself behind limits we can never cross? Right now, at this very moment, ancient photons are reaching your eyes. They began their journey when the universe was young, dense, and unfamiliar, when the first structures were only beginning to form. But while that light was traveling, the universe did not stay still. Space itself stretched, distances expanded, galaxies drifted away, carried by the slow but relentless growth of the cosmos. By the time that ancient light finally arrived here, the place it came from was no longer where it once had been. It had been carried far beyond what intuition would ever suggest. This is the uncomfortable truth we rarely stop to consider. The universe we see is not the universe as it is. It is the universe as it was. And even more unsettling, most of the universe may already be lost to us forever. There exists a boundary around us, not a wall, not an edge you could ever touch, but a limit defined by time, light, and expansion. A horizon beyond which information can never reach us, no matter how advanced our technology becomes, no matter how long we wait. We live inside a growing bubble of visibility, a cosmic island surrounded by an ocean we will never explore. And the strangest part is this: that boundary is not fixed. Some parts of the universe are slowly slipping away from us right now. Galaxies are crossing invisible lines, fading from reach, their future forever disconnected from ours. So what exactly is this boundary? Why is it so much farther than the age of the universe suggests? And how is it possible that the universe can be both finite in what we see and potentially infinite beyond? To understand this, we must first confront the most misunderstood concept in modern cosmology: the observable universe. At first glance, the idea seems simple. The universe is 13.8 billion years old. Light travels at a fixed speed, so you might expect the farthest thing we could possibly see to be 13.8 billion light years away. But that intuition is wrong, very wrong. The observable universe is not a sphere with a radius of 13.8 billion light years. It is nearly 3.5 times larger. Its radius today is about 46 billion light years. This is not a trick of measurement. It is not an error in our instruments. It is a direct consequence of how space itself behaves. Here is the crucial detail most explanations skip. Light moves through space, but space itself is not static. While photons travel at a constant speed, the fabric of the universe stretches beneath them. Distances grow while light is still in transit. Imagine a photon leaving a distant galaxy when the universe was young. At that moment, the galaxy might have been only a few billion light years away. But as the photon moves forward, space expands behind it. The destination retreats. The path lengthens. The finish line keeps moving. By the time that photon finally arrives here, the galaxy that emitted it is no longer a few billion light years away. It is tens of billions of light years distant. This is why the observable universe is so vast. Not because light traveled faster, but because the universe expanded while the light was en route. And this leads to a deeply unsettling realization. There are regions of space we can see, but can never reach. No spacecraft, no probe, no future technology will ever cross those distances. Even if we could travel at the speed of light, the universe would carry those destinations away faster than we could chase them. We are not looking at distant places. We are looking at ancient moments. Every galaxy you see is a memory. Every deep space image is a fossil. And the farther you look, the deeper into the past you are forced to stare. This is why the observable universe is not a map of reality as it exists now. It is a historical archive, incomplete, biased, and slowly changing. The boundary of this archive is called the observable horizon. It marks the greatest distance from which light has had enough time to reach us since the beginning of the universe. Everything beyond it may exist. It may contain galaxies, stars, and structures just as rich as our own region. But it is forever hidden. No signal from those regions has ever reached us, and none ever will, not because of distance alone, but because of time. Here is the uncomfortable question that follows. If most of the universe lies beyond what we can ever observe, how confident can we really be about the universe as a whole? Are our cosmological laws universal, or are they local descriptions of a much larger reality we will never access? We often speak as if the observable universe is the universe. But it isn't. It is only the part that had enough time to reveal itself. And even that window is deceptive. Because while the observable horizon slowly expands, another boundary is quietly closing in, one that determines not what we can see now, but what we will ever be able to see. And this next horizon is far closer than most people realize. Space is stretching while light is traveling. To truly understand why the universe appears so much larger than its age suggests, we need to let go of a deeply ingrained idea. We tend to imagine space as an empty, motionless stage, a fixed arena where objects move through it. But space is not a passive background. Space is active, dynamic, and relentlessly stretching. When light travels across the universe, it is not moving through a static void. It is moving through a fabric that is expanding in every direction, at every moment. A useful way to picture this is not as a race, but as a struggle. Imagine a photon, a single particle of light, leaving a distant galaxy shortly after the universe becomes transparent. It begins its journey toward us at the fastest speed anything can possibly move. But the path it must cross is changing. As the photon advances, new space continuously forms between it and its destination. The universe adds distance faster, the farther apart two regions already are. So the photon is not simply traveling across space. It is fighting against it. This is why a simple calculation, speed of light multiplied by age of the universe, fails so dramatically. It assumes the distance is fixed. The universe behaves less like a rigid road and more like a moving walkway, one that accelerates as you move farther along it. For nearby regions, the expansion is gentle. For distant regions, it becomes overwhelming. And this leads to a counterintuitive truth. Some of the light we see today was emitted by galaxies that were already receding from us faster than the speed of light. That statement alone sounds like a violation of physics. But it isn't. Nothing locally moved faster than light. No galaxy broke the cosmic speed limit. Instead, the space between us and those galaxies expanded faster than light. This distinction is crucial. The laws of physics limit how fast objects can move through space. They place no limit on how fast space itself can expand. And on the largest scales, it does. Right now, there are galaxies whose recession speed, driven entirely by cosmic expansion, exceeds the speed of light. Not because they are flying away like rockets, but because the space between us and them is stretching at an extreme rate. And here is where things become deeply unsettling. Some of those galaxies are still visible to us. We are receiving light they emitted billions of years ago, when they were closer, when the expansion between us was weaker. But if those galaxies were to emit light today, that light would never reach us. It would be dragged backward by the expansion of space, losing ground faster than it could advance. In other words, we are seeing galaxies that are already causally disconnected from us. We are observing their past, but their present and future are forever inaccessible. This raises an uncomfortable question. If the universe allows regions to become permanently unreachable, even while remaining visible for billions of years, at what point does seeing something stop meaning it is part of our universe in any practical sense? Is a galaxy still part of our cosmos if no signal it sends now can ever reach us? Or are we simply watching ghosts, images frozen in time, slowly fading as the universe pulls us apart? The expansion of space does not just increase distances. It reshapes causality. It decides which events can influence us and which are lost forever. And in the earliest moments of cosmic history, this expansion was not gentle at all. It was violent, extreme. And it permanently altered what we would one day be able to observe. To understand why the universe looks the way it does today, smooth, vast, and strangely uniform, we must return to a moment when space itself expanded faster than anything we can currently imagine. A moment known as cosmic inflation. Inflation changed everything. To understand why the universe looks the way it does today, we need to return to a moment so brief that it barely qualifies as time at all. A fraction of a second after the universe began, something extraordinary happened. Space didn't just expand, it exploded outward. This phase is known as cosmic inflation, a period when the universe grew faster than light, faster than intuition, faster than anything we observe today. In less than a heartbeat, regions of space that were once unimaginably close were torn apart and flung across enormous distances. And this matters more than it sounds. Because inflation didn't just make the universe bigger, it set the limits of what we can ever observe. Tiny quantum fluctuations, microscopic variations in density, were stretched to cosmic scales. These ripples became the seeds of galaxies, clusters, and the large-scale structure of the universe. But inflation also created a permanent separation. Some regions were pushed so far away so quickly that no signal from them could ever catch up to us. Not then, not now, not ever. Those regions may still exist. They may look very much like our own, but they were effectively erased from our observable reality almost at birth. This leads to a deeply unsettling idea. The universe may be vastly larger than the part we can see, not just in space, but in history. There may be regions that evolved entirely beyond our causal reach from the very beginning. Different initial conditions, different cosmic histories, possibly even different physical outcomes. And we would never know. Everything we call the universe is shaped by a brief, violent event that lasted less than a second, yet determined the fate of visibility for all time. But even inflation did not create the final boundary. Another limit emerged later, quieter, slower, but far more cruel. A boundary that decides not what we can see now, but what we will never be able to see, no matter how long we wait. The cosmic event horizon. There are two different edges to the universe, and confusing them changes everything. The first is the observable horizon, the boundary of what we can see today. The second is far more disturbing. It is called the cosmic event horizon. This horizon marks the maximum distance from which light emitted now or in the future will ever reach us. And it is much closer than the edge of the observable universe, roughly 16 to 18 billion light-years away. Beyond this distance, galaxies are not just far, they are lost. Even if they shine forever, even if the universe lasts eternally, no new information from them will ever arrive here. Their future is causally disconnected from ours. We may still see their ancient light today, light emitted billions of years ago when they were closer, but their present is already beyond reach. This creates one of the strangest illusions in cosmology. We can observe galaxies that no longer exist for us in any meaningful sense. From our perspective, they slowly fade. Their light stretches toward redder wavelengths. Time appears to slow for them. Their evolution seems to freeze. Eventually, the last photons arrive. And then, silence. Those galaxies do not explode. They do not vanish dramatically. They simply slip beyond the horizon, leaving behind only an image of what they once were. From their perspective, the same thing happens to us. They would see our galaxy slow, redden, and fade. No warming, no final signal, just permanent separation. This is not science fiction. It is the measured, predicted future of an accelerating universe. And it raises an uncomfortable final question, one that has nothing to do with equations. If the universe is steadily isolating every region from every other, if visibility is shrinking, not expanding, then are we living at a special moment? A brief window when the universe is still visible, connected, and understandable? Or are we already too late to see most of what truly exists? The edge of the universe is not a wall in space. It is a boundary in time, causality, and information. We are not trapped by distance alone. We are limited by the history of expansion itself. The universe may be vast, beyond imagination, but only a fraction of it will ever be part of our story. Everything else is already slipping away. So the real question is not how big the universe is. The question is this: how much of reality have we already lost without ever knowing it was there? And if the universe continues to accelerate, what will future civilizations believe the universe is once almost everything has disappeared from view?